Okay, so this video is on one-digit long division. So a few things about this. Let me just talk in general about long division. So long division is, so once you get sort of beyond sort of small numbers in doing division, this algorithm really helps us do that. So that's one thing. If I just have a, I would say let me do a relatively simple, I don't know, 127 divided by 8. So this might be a little challenging for mental math, but it's a nice problem for long division to try to figure out both the whole number quotient and then any remainder that there might be. But as we're going through long division, later on we're going to see there's some really links between long division and fractions in terms of taking a fraction and turning it into, say, a decimal. And we can also do kind of the reverse as well. If we've got certain repeated decimals, about turning them into fractions, how that's all related. The other thing about long division is, and this is, I think, one of the really key things for students sort of understanding this at the basic level, is you go on into higher level mathematics beyond the K-5, and long division still plays a role. The classic example is if I have some polynomials, and those are like powers of x and so forth, we can use long division to what is called reduce those. And it's really the same algorithm. Okay, as we're going to go through this, we're going to sort of also go through what is helpful for students going through long division. So I'm going to start with one-digit long division in the next couple of videos here. And then what we'll often do is once we get to two-digit, it gets a little bit more complicated. So we're going to take a little pause and do a little bit of approximation and understanding approximations before we finish off the algorithm. And it takes a few years to get through the curriculum to really nail down long division completely. Okay. So the first thing I really want to do, excuse me, let me grab some notes, is let's say I've got an example like this. So let's divide 94 cents evenly between two people. So not a difficult problem to do, but what I'm going to do is I'm going to use a chip model to actually do this. So let's examine a chip model. So like I've done before is I'm going to write down 90, 1, 2, 3, 4. Okay, and really what we're going to do is we're going to do the opposite of what we did for chip models for multiplication. And that should make sense because long division in many ways is the missing factor in multiplication, so it's the opposite of multiplication. So here's what I'm going to do, is I'm going to take these coins. So again, imagine I've got 9 dimes and 4 pennies, and I want to just divide them into 2 piles. So here's what I'm going to do, is I'm just going to go 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. And so I just divided them in 2 piles, and maybe let's do that to really make it clear. Okay, so notice I've crossed them out, and all I've done is I've just moved them down. And hopefully I think that that's fairly clear. Now what I'm going to do is I'm going to take this, and I can't divide a dime in 2, so I need to rebundle it. So I'm going to take this and turn it into 10 pennies, but I'm going to do it in such a way that goes like this. 1, 2, 3, 4, 5, 6, 8, 9, 10. So I'm going to cross that out. I'm going to show this rebundling. Right, so I've taken that dime and turned it into 10 pennies. Now I still have 4 pennies left. So 1, 2, 3, 4. Okay. And I've got that. All right. So does that make sense? All right, so first of all, again, all I'm doing is I'm going to take, this time, this goes from left to right, so it's a little bit weird, but we'll explain this. So I'm going to take this and divide it into the number of groups that I have. Right, I have 2 groups, so I'll evenly do the 2 groups. And then when I get to the result that I can't divide 1 into 2 groups, I'm going to unbundle and do this. Okay, the other thing to think about is, hey, if I do this in the opposite direction, really what I've done is if I take these, right, if I've got 2 times whatever this is 47, right, then what I did is the opposite of this, I would put it down here, and that would give me 94. So 2 times 47 would be 94 from this. So I'm doing exactly the opposite of the chip model for multiplication. All right. So I should say this is 90 or 47, because each of these 2 groups is 47. Okay, now let's remember a little bit of long division. Okay, so here's what I want to do is I want to go, what times 2 gives me something not over 9, but just under 9 or equal, exactly 9, right? And this is 4, and 4 times 2, I get 8, and then I subtract. Okay, so a couple things here. This 4 represents that group of 4. That 8 represents the whole group that's evenly split of 8. That 1 is the one unbundle that I have. Okay. And then I'm going to bring, and this is not 97, but 94. I know somebody through the ether was trying to tell me that I made a mistake. And so 2 times what gives me 14? That's 7. 14, 0, right? So that 7 represents that 7. That 14 represents everything. And everything goes in evenly, so I get a 0. Okay. Let me do one more. And I'm going to do a bigger one. I'm going to divide 524 evenly between 3 people. And I should say one of the things that this is, right, I should have said this at the beginning, is this is partitive division. We know the number of parts or groups. Okay. Another video I'm going to show talks about how do you do the measurement interpretation. So I've got 100s, 10s, 1s. This may need to go down a little lower. Let's give ourselves plenty of room. 520 1, 2, 3, 4. Okay. So the first thing I'm going to do is I'm going to break, I've got 3 people, so I'm going to break to 3 groups. Okay, so 1, 2, 3, 1, 2, 3, and I have 2 left, so I can't do any more of those. So I'm going to take this guy and do it into 10. 1, 2, 3, 4, 6, 7, 8, 9, 10. Okay. I like to always show either bundles or unbundles and show which is crossed out and where they go or come from. So now I've got that one. 1, 2, 3, 5, 6, 7, 8, 9, 10. Okay, and notice that I'm trying to keep them so the grouping is the same. So that's there and that's crossed out. And then I'm just going to put one of these guys down there because I need, right, that's got 7, 7, 7. So that just moved down there. I don't feel like you could show where that goes, but I think that's okay, like that. Okay, so this one now, right, since everything's even here, I'm going to do the same thing over here and do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2. Okay. And what does this show us? Okay, and then these are going to be 2 remainders. So what do I have for each group? I have 1 for each group. I have 1, 2, 3, 4, 5, 6, 7. And I have 4, right? And I have remainder 2. Okay, remember again, what is this? It's the exact opposite of multiplication here. So if I did 3 times 174, it would be the bottom, and you would regroup to get the top. So it's exactly the opposite. Okay. Okay, let's look at the long division of this. All right, so I want to, 3 goes into 5 how many times? Well, 1 with 2 left over. Okay, that represents, there's 1 in each group. That 3 represents the total in the hundreds. Okay, 2 are the 2 remainders here that we need to unbundle. Let's bring that down. 2. 3 times what is close to that? That's a 7 and 21. And I subtract. Okay. So that 21 is the, so that 7 is the number, right, in any one of these 3 rows. The 21 is the total in the rows. And the 1 is there was 1 left over. So bring down 4, 4, and 2. Okay, that 4 is the 4 in each of these 3 rows. That 12 is the total in the 3 rows. That 2 are the 2 left over. Okay, good. So these are a little bit trickier, but just takes a little bit of practice. They're also, I think, you know, either doing up the tens or even the hundreds is not too bad. As long as this is a sort of small 1-digit number, 2, 3, 4, maybe even 5 type of thing. Even getting up into divisible by 8 is kind of a crazy thing. It still works. It all works the same way. It's all that. Okay, but again, understanding the link between the chip model and long division is huge. So that takes care of that. Again, how chip models work.